we want to do a DC calculation for a MOSFET. So in order to do this, we have to first of all write down what our basic equations are. So with this MOSFET, we're going to go ahead and use Kp equals 0.1 and the threshold voltage as 1.5. So we have two regimes. One is triode and one is active. So let's start with triode. So in triode, our current is going to be equal to Kp times VGS minus V threshold times VDS minus VDS squared over 2. And this is valid if VDS is less than VGS minus V threshold. Okay, and then we're going to have active. And in active, we have ID equals 1/2 Kp, and then we're going to have VGS minus VTO squared. Okay, so these are going to be our two regimes. Oh, and then this is if just the opposite is going to be VGS minus VTO. Okay, so we look in here, and I don't know what my current is, and if I don't know what my current is, I don't know what my VDS is, so how do I know which regime it is to start off? So what we're going to have to do is, first of all, assume that it's in active. So we're going to assume that it's in active and then solve from there. So when it's in active, you can see right here, using this equation right here, that it's completely independent of VDS. So that means I can come in and I can just calculate ID directly. So this is going to be equal to 1/2 our Kp, which is 0.1, and then our VGS, which is going to be equal to 2 minus our threshold 1.5 squared. And so then this is equal to, so that's equal to 0.0125 amps or 12.5 milliamps. Okay, and then from there I can calculate what my VDS is. So VDS is going to be equal to 10 minus 100 times 0.0125. So this is equal to 8.75. And then we have to come back and check our assumptions. So we're comparing 8.75 to 2 minus 1.5, which is our VGS minus our VTO, and then 8.75 is definitely larger than 0.5, and so check, we were in the right regime, so we are done. Well, let's go over to Ltspice to check this out and see if it works. So you can see here that I built an ideal MOSFET with a VTO of 1.5 and a Kp of 0.1. These are the only parameters that we're passing, so it's going to be pretty close to ideal. So we're going to run this. And we look, and you see here is my VDS 8.75. Here is my ID of 0.0125. So everything works out. Well, now let's try this again. But now let's just change our circuit so that it's going to throw it out. So we're just going to make this 1,000 now. And let's copy this over. Okay. Make that a little smaller because that's a little bit on the large size. Okay, and then we're going to go through the same thing the same way. So we're going to assume active, which means that I can just come up here and grab all of this because this stays exactly the same. because all we changed was our voltage. I mean, our resistance. So we have this, and then we have VDS is going to be equal to 10 minus 1,000 times 0.0125, which is going to be equal to, so then this is equal to this is equal to minus 2.5. Well, minus 2.5 compared to 2 minus 1.5, this is less than. So we see that our VDS is going to be less than VGS minus VTO, which means that we're actually in triode. Okay, so now we're going to go and have to use our triode equation. So now we have ID is equal to KP times VGS minus VTO times VDS minus VDS squared over 2. Those are our equations. Well, we have to plug in the equation for VDS. So this is going to be KP VGS minus VTO. And then my VDS was 10 minus 1,000 times ID minus 10 minus 1,000 times ID squared over 2. Plug in the values that I have. So I have ID equals 0. What are we using? We're using a KP of 0.1. 0.1 times, and then this is going to be 2 minus 1.5 times 10 minus 1,000 ID minus 10 minus 1,000 ID squared over 2. Well, now I have a big quadratic equation that I have to solve for ID. Well, let's just go plug all this into Wolfram Alpha to do my nonlinear solve. And I don't even have to come close to spelling it right. Thank goodness. Okay, so then we're going to go x equals 0.1 times, and then we had 0.5. Well, let's just plug all this in so we can see. So we're going to go 2 minus 1.5 times 10 minus 1,000 times x minus 1/2 times 10 minus 1,000 times x squared, in parentheses, solve this. Let's see, does that look good? That looks right. So we come down here and we have two solutions. Well, what are our two solutions going to be? So let's start with this one as my current. So that's 9.92 milliamps. So let's go back here. Well, let me grab that. Okay, so that's my ID. So then we're saying that VDS is going to be equal to 10 minus this times 1,000. Okay, and so then that is going to be equal to, so that's equal to 0.7551. And then we're comparing my VDS 0.7551 to my VGS minus V threshold, and you see that this is larger, which means, well, that's wrong because it was supposed to be smaller if I'm in triode. So let me go back and check my other solution. So in this case, I have this number. So now we have VDS. We have VDS is equal to 10 minus this times 1,000, which is equal to, let's see, which is equal to 0.2649. So we have 0.2649, and then we have our 2 minus 1.5. So 0.2649 compared to 0.5. And this is definitely smaller than that. So check, we did it, and then that is our answer. So that means our answer is ID equals 0.974 milliamps, and VDS is equal to 0.2649. Okay, let's go to Ltspice to check this. So we go over here, we change that to 1,000, and we run this. Okay, so we see here that my ID is, okay, there's my ID right there, and here is my VDS. And so we would check and say, is VDS minus my gate to source? So here's this. So you see you have to do it by hand and make sure that it is actually in Triode. So you can kind of see that we now know how to do it by hand, and then we can check it in Ltspice. Now, most of the time going through all of this, you can see is kind of messy and takes some problems and some time. So typically we're just going to go straight into Ltspice and do it, but we need to check and make sure to know whether it's an active in Triode by looking at the voltage to drain to source compared to my gate to source.